In this video, we will talk about rotational lines associated with vibrational transitions called vibrational rotational spectrum. So that's simultaneous rotation and vibration of a molecule. So we can see that each vibrational level, because it's higher in energy, has rotational levels within it. From the point of view of spectrum and calculating detailed obtaining detailed information, we can consider this rotation as a rigid rotor rotation and the vibration as an harmonic vibration with all the rules applied. So for rigid rotor, harmonic oscillator, the energy is V plus half times the vibrational frequency, and for the rigid rotor, the energy levels are Vj into J plus 1, where the vibrational frequency is related to the force constant and reduced mass. And B, the rotational constant, is h over 8 pi squared IBC, where IB is the moment of inertia along the B axis. And then the selection rules in the harmonic oscillator is that V can, the vibrational quantum number can change by plus or minus 1, and the rotational quantum number can change by plus or minus 1 as well. We can also consider, a V from 0, a transition between a particular vibration is a pure rotational transition. So take for example, there's a rotation that goes from 1 to 2 here. That's pure rotational translation. So a vibrational rotation involves energy levels in different vibrational states. We can also consider an harmonic oscillator, and the energy level, S is the energy level, is called vibrational rotational term. The energy level now involves the vibration energy that includes the different anharmonicity terms and the energy level of a rigid rotor. And in this case, our selection rule includes the fundamental and overtones, since we're considering an harmonic oscillator. Then in the third case, we can have an harmonic oscillator, the non-rigid rotor approximation. Now, in the two previous cases, the vibrational and rotational energies were treated separately, like the Oppenheimer approximation. However, in the harmonic oscillator non-rigid rotor, if you recall, when we're talking about non-rigid rotor, we said vibration affects it. We cannot treat it as just an independent motion. They are not independent of each other. So we have the energy of the rigid rotor, non-rigid rotor, that's Bj into J plus 1 minus D, J squared into J plus 1 squared, where D is the centrifugal or distortion constant. Then we have the energy level for an harmonic oscillator to the third term. And then we have a coupling term that involves the vibrational levels and the rotational levels. The coupling term. The selection rules here are delta V. The vibrational can change by plus or minus 1. Overtones are allowed. Here we also have delta J changing by plus or minus 1, and in very rare occasions delta J being equal to 0. So that would be like from J equals to 1 to J equals to 1. Now the result of vibrational rotational spectra, if we follow our different lines, so this is a lower vibrational level, that's a higher vibrational level with several J states, is that you have, with each transition going from this is a transition, you have lines on the side. The lines represent what we call spectral branches. So spectral branches are rotational fine structures that are associated with a band. So let's take a good look at it again. So this is a lower energy level, vibrational energy level. So we can have transition from this vibrational lower level to this vibrational excited level. And while that is taking place, we can have additional rotational changes. So if J can change by +1 or -1 or 0, that's in rare cases, it means that we can have J, this picture is not very clear, so J going from 2 to 3, from 3 to 4, so that's a delta J equals +1. We call that R branch. Again, branches are rotational fine structures associated with a vibrational band. We can also have situation where J starts from 2 and ends at 1, starts at 3 and ends at 2, starts at 4 and ends at 3. So the change in J value now is -1. It originates from a state J and terminates in a state J -1. When delta J is -1, we have JP branches. So the one that's so represented is from 2 to 2, 3 to 3, so that's delta J equals to 0. We call that the Q branches. So the Q branches are not usually common, but at least this is a source of broadening that we see in a vibrational spectrum. So the P branches appear at lower wave numbers because J is -1, and the R branches appear at higher wave numbers, and then the Q branches just coincide with the center of the band called band center. So the center of the band is where the vibrational transition takes place. So this is an example for NO spectral where the Q branch is allowed. Another example where the Q branch is not allowed. So we have the R branch, which is at higher frequencies, and then the P branch at lower frequency. For NO spectra too, so the R branch is also at higher wave numbers because wave numbers is directly proportional to frequency, and then the P branch is at lower wave numbers. Okay.